Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to go over liquid water and water solutions. So let's get into this. Let's start with liquid water. Well, what is water? Water is H2O. It has two hydrogens bonded to an oxygen, and if we write the Lewis-Dot structure, it looks like this. So you might be familiar with the Lewis-Dot structure. So the central atom oxygen has two hydrogens bonded to it and it's got two lone pairs. That's four total bonding groups. I'm sorry, not bonding groups, but total electron groups is four, two bonding, two non-bonding. And so according to Vesper theory, based on the fact that these electron groups are all negative groups, they want to be as far apart as possible. And so we would predict that water has a tetrahedral structure. And so if we draw the shape of it, it would look something like this in a 3D form. Forgive my drawing. So this hydrogen is coming out of the board, that dark wedge. This hash wedge is going into the board, and then these two lone pairs are in the plane of the board itself. So you get a bent shape. If you rotate it, you can see it this way here. So you can see that the angle between the hydrogens here is a 105-degree angle. So you have the hydrogens bonded or bent to one side of the molecule. So this gives the polarity of the molecule because we know that oxygen is much more electronegative than hydrogen. It's going to attract those bonded electrons closer to the oxygen so that the electron density is going to be more around the oxygen than it is around the hydrogens, giving a partial positive to the hydrogens and a partial negative charge to the oxygen written here. So this is your delta plus small lowercase delta. This means partial positive charge. So this has a partial positive on the hydrogen here, partial positive on the hydrogen here, and the oxygen has a partial negative. So you can see that one side of the molecule is going to be a partially negative side, one side is going to be partially positive. So that gives it polarity. So remember, like magnets, you have a positive side, you have a negative side. We call those poles. So a positive pole, negative pole. So that's what you see here. Polarity, positive pole, negative pole. So why is this important? Well, it's important because this allows for water molecules to attract each other. So the positive side of one molecule of water can attract the negative side of another water molecule. And so that's what I have drawn here. So here I have one water molecule. Here's got the oxygen on this side, partially negative, and then on this side you have the partial positive hydrogens. And then on this side, this water molecule, you have the partial positive hydrogens on this side and the partial negative oxygen on this side. And so when they're facing in this sort of orientation, the partial positive hydrogen of one molecule is going to be attracted to the negative electrons on the oxygen here. So this is a partial negative. So the lone pair electrons are going to be attracted to the hydrogen on another water molecule. So the oxygen here on this water molecule will be attracted to the positive hydrogen on another molecule, and that creates attractive force between them. And this is called an intermolecular force, right? Inter meaning between, molecular referring to molecules. So intermolecular is between the molecules, right? So here, this is not an intermolecular force, it's an intramolecular force, meaning within the molecule. So this hydrogen bonded to the oxygen is an intramolecular force. So this is much stronger here than here, but this is a relatively strong intermolecular force. We call this the hydrogen bond. Again, the hydrogen bond is between molecules, not within the molecule. So here, this OH here is not a hydrogen bond. We don't call that the hydrogen bond. Here, between these molecules. So what's important to realize about the hydrogen bond is that the hydrogen bond is strong enough to keep these water molecules at the same average distance from each other. So they're not really going to move far apart from each other. It keeps them together. This is why water is a liquid at room temperature than it is a gas, right? So, excuse me. So the hydrogen bonds of the water molecule is strong enough to keep them together, keep them relatively close at the average same distance apart, but they are weak enough to allow them to break the attractions between molecules and form attractions with other water molecules. So this allows them to kind of, flow and move. So water molecules are able to move past each other because these hydrogen bonds can be broken relatively easily and reformed with each other. So these hydrogen bonds aren't so strong that it just keeps the water molecules in one space. Therefore, it's not a solid, right? So it's a liquid. So this allows the water molecules to move, locomotion, move from place to place, and get translational motion is another term that you can use. So that is the properties or understanding of liquid water. This is really important to understand when you're talking about solutions. So let's go ahead and talk about solutions. So when we talk about water solutions of ionic compounds, and remember, an ionic compound is a compound made up of ions. Ions have charges, right? They can be molecular. They could be like a molecule with a charge, like a polyatomic ion, or it could be a single atom, a monoatomic ion, like sodium and chloride ions, right? So here, when we're talking about a solution, what we mean is a homogeneous mixture. So these terms are interchangeable. When I say solution, I'm referring to a homogeneous mixture. And what is a homogeneous mixture? Let's remind ourselves of that. So a homogeneous mixture is a mixture between two substances that, when you look at it, really looks like one substance. It's uniform throughout. That's another term that's used, uniformity, right? So when you mix two substances together, if they are uniformly mixed together, that means they are evenly spread out. Excuse me. They are evenly spread out through each other, so that way they are completely evenly mixed and it's uniform, so that when you look at the mixture, it doesn't look like a mixture. It looks like one substance. A couple of examples. Salt water, right? You throw some salt, NaCl, in the water, it dissolves, it spreads out evenly throughout the water. When you look at it, it doesn't look like a mixture of salt and water. It looks like just water, right? You can't really see that it's a mixture. Another example is something like an alloy of metals, right? So if you take brass, for example, or bronze, right? When you look at the brass or the bronze or steel, for example, it looks like it's one type of metal, right? It looks like it's one substance. But in reality, it's a couple of different substances mixed together, right? So it could be copper and zinc, for example, mixed together, and it looks like, and you wouldn't be any of the wiser, because when you look at it, it doesn't look like, oh, here's copper, here's zinc, oh, it's a mixture. No, it looks like it's one thing, right? So that's what we mean by a homogeneous mixture, a uniform mixture, where the substances are spread and mixed thoroughly throughout, evenly throughout the mixture. So when we talk about homogeneous mixtures or solutions, as I'm pointing out, this doesn't apply only to liquid and solid mixtures, right? As I just pointed out, you can have two solids mixed together, like two metals mixed together, and that would be a homogeneous mixture as well. So we're not really, when we use the terms solution, I know what comes to mind is more of like a liquid mixture, right? When I throw alcohol and water together, right, for example, that would be a solution. Or if I throw salt and water and it mixed together and I still have a liquid mixture, that would be a solution. That's normally kind of what we think about when we hear the word solution, right? But two solids mixed together is technically, according to science and chemistry, is a solution, right? Air is a mixture, right? Air has oxygen in it. It has nitrogen, hydrogen. It's got all these gases in there, carbon dioxide, all mixed together evenly. So therefore, air is a solution, right? It's a homogeneous mixture. When we use the term aqueous solution, that's a little bit more specific. So this isn't really equal. I shouldn't really have that there, right? So let's kind of part that out a little bit. Aqueous solution is technically going to be where you have one substance mixed in with water. Aqueous refers to water. So in order to have an aqueous solution, you must have something mixed with water. It has to have water in it. So salt thrown in water is an aqueous solution. Alcohol thrown in water mixed together is an aqueous solution. Sugar thrown in water, dissolved in water, is an aqueous solution. So aqueous means something is dissolved in water, right? So, okay, so there's the terms. I just want to clarify terms. So let's talk about ionic compounds being dissolved or in water, aqueous solutions involving ionic substances. So here I have a crystal. This is my NaCl. We'll call this, well, this is my NaCl crystal. So I've got positive sodiums and negative chloride ions alternating each other in the crystal. So here, every positive sodium is surrounded by 6 negative chloride ions, and each chloride ion is surrounded by 6 positive sodium ions. And so I throw this crystal in water. So what's water going to do? This is important here to keep in mind that we have this positive side and negative side, negative oxygen, positive hydrogens. What's that going to do? Well, remember, opposites attract, right? So positive is going to attract a negative. Negative is going to attract a positive, right? So in this case, these charges are strongly attracted to each other. These are really strongly bonded together, right? But what does water do? These water molecules have a positive and negative side. So what they're going to do is they're going to be attracted to the ions. So what I have here, the negative ion here, this chloride ion, is going to be attracted to, or I should say that the water molecules, the positive side, notice the partial positive hydrogens are going to be attracted to the negative ion, the chloride ion. And what's that going to do is the water molecules are going to start to disrupt the attractive forces between the ions here and start to pull the chloride ions out of the crystal structure. So they're going to weaken or disrupt the attractive forces between the ions and start to create attractive forces or bonding with the ion itself. And so you'll get these water molecules creating kind of a sphere around the negative ion. And you'll notice here that all of the positive hydrogens are facing towards the negative hydrogen. So they are positioning themselves such that the positive side of the molecule is facing towards the negative ion here. And so it encapsulates it, and then through the motions, it moves it away, right? So again, this is within water, right? And so again, the same thing is happening with the positive sodium ion. So again, the water molecules, the negative oxygen of each of the water molecules are going to be attracted to the positive ion. Again, disrupting the attractive forces in the crystal, as at the surface, of course, right? Because these inside the crystal aren't going to be exposed to the water. So it's going to be these on the surface are the ones that are exposed to water molecules. So the water molecules are going to kind of pull them apart. And they do that by disrupting the attractive forces between the ions. They're going to start to create these hydrogen, no, I shouldn't say hydrogen bonding, but these attractive forces, these bonds with the positive sodium and the negative, partially negative oxygens on each of the water molecules. And again, you can see that the water molecules here are facing such that the oxygen is pointing towards the positive ion. And so again, they're encapsulating and surrounding the positive ion. And so they're going to start to move that away. And this is how dissolving happens. Now, do all salts or ionic compounds dissolve in water? No. It's going to be a balance between what is called the lattice energy here, the amount of energy here that's keeping the ions together, versus the attractive forces between the molecules themselves and the attractive forces between the water molecules and the individual ions themselves, right? So if the bonds between the water and the ions is much greater than the bonding between the ions and the bonding between the water, then you're going to get dissolving. If the bonding in the crystal is stronger than that between the bonding of the water and the ions, then it's not going to dissolve. So it's a balancing between attractive forces here. And so that's what happens with ionic compounds dissolving in water. Now, the last thing I want to talk about is things called solute and solvent. So let me write that on the board. Solute versus solvent. Now, solute is what we think of as the substance that is being dissolved in the solvent, right? So when we want to draw a distinction between these two, we think of the solute as that which is being dissolved. Whatever is being dissolved is the solute. Whatever's doing the dissolving is the solvent. So when we're talking about aqueous solutions, water is the solvent, right? So we're taking some substance, we're throwing in water, and it dissolves in the water. So if it was, for example, sodium chloride, salt, then the sodium chloride is the solute being dissolved in the water, and the water is the solvent. So anytime you have an aqueous solution, water is the solvent. Water is doing the dissolving, and whatever is dissolved in the water is the solute. So that is an important distinction. So solute is being dissolved. Solvent is what is doing the dissolving. Okay. Now, you can have this. It doesn't have to be in water, right? If it's not in water, then the way you understand solute and solvent is a little bit differently, but it's quite related. So if we're not talking about dissolving something in water, then what we mean by the solute is that which is in less quantity of. It's the one we have less of, and the solvent is what we have more of, right? So for example, if, what's a good example? Let me think of a good example. Yeah, so here's an example. Let's say I have, I'm mixing pentane with hexane, so two nonpolar substances, right? So I have pentane. Let's say my mixture is 5% pentane, 95% hexane. So in that case, the major substance, the one that I have a majority of, is the solvent. In this case, hexane. Since 95% of my mixture is hexane, that's considered the solvent. And since the pentane is only 5% of the mixture, then that's considered the solute. So whichever one I have less of, or whichever one is the minority substance or the minor substance, that's going to be the solute. And whatever is the major component of the mixture, or the one that I have the majority of, is going to be the solvent. And so that's how you understand solute and solvent in mixtures that don't involve water. And so that's it for this video. I hope this was helpful. If it was, then please like the video, share the video with your friends, and also hit that like button down there somewhere, I think. And also subscribe to my channel. Hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. I want to hear from you. Tell me what you think. Ask me questions. If you have a particular topic you want me to cover, let me know. If you have a particular question or problem you want help with, then put that down below. I'd love to help you with that. Thanks for joining me and have a great day.